Hello, welcome. We'll continue our discussion on 1D optical waveguide, and we have discussed earlier already how to solve the modes and what would be the field distributions and whatever the phase velocity and what is the cutoff, how many modes will be supported by a given slab waveguide or planar waveguide structures. And today we are going to discuss that if your operating wavelength differs, operating frequency omega differs, you know that omega operating wavelength we consider any mode. If you just consider in T polarization, we have discussed something like that, that only y component will be there, Ex, and then e to the power, this is a y unit vector, e to the power j omega t minus beta z, and if it is mth mode I can write m like this. So, and also we know how to find out if it is T polarization, how to find out also this other components like magnetic field components like say H x and H y, and all the components say 0 U I 0 electric field and magnetic field component you can consider H x 0 H y, and all of them are actually x dependent because x direction it is confined, okay, x function of x, and along with that will be a propagating with a phase omega t, time dependent phase, and propagation direction beta z, and beta equal to nothing but omega by c n effective. And if it is different mode, all this field distribution will be different, and associated mode propagation constant also will be defined like that, omega by c n effective m. Okay. So, all this we discussed, they are actually function of a given frequency omega equal to 2 pi by lambda c. Okay. So, we will be just following that one. If frequency changed, then what happens? So, for that purpose we just go back to the basics again, the device structure, silicon on insulator device structure, wafer structure. If you see, it is a 3 layer medium, and of course, in the bottom there will be substrate silicon or handling wafer will be there, handling wafer, and then on the buried oxide silicon dioxide will be there, which we consider NS, and then your actual device layer, this is device layer which is called silicon on insulator, refractive index ND, and cover dielectric also can be silicon dioxide ER. Also one can consider, sometimes people use also Si3 and 4, which is having refractive index also lower than silicon, and approximately refractive index is 2, something like that you can also consider here. Okay. For our discussion, most of the time we will be considering this as a AR, but only refractive index difference you can consider, something like that. So, this is a slab waveguide, and you are considering that this is x axis, this is z axis, and y axis you are considering infinitely extended. What is happening in that direction you do not know, at least you know that wave is having a wave vector that will have k x component, and you will have also z component, k z component, and k x component actually contributes the standing wave along x direction. Here in this direction it will be confined, and k z component actually helps to propagate in the forward direction, which is actually nothing but the beta, whatever mode you are getting, that will be propagating along the beta direction. Okay. So, now if we just think of the same thing whatever we discussed for T polarization, this is the field components E y, H x, H z. If I just concentrate on E y will be x dependent, it will be j omega t beta z. That is what we learned so far. Orange color for TM polarization, green color is for T polarization or T mode, and for TM polarization you have electric field will be in the xz plane. That means it is actually, it has a normal component along x direction in the interface, and magnetic field HY is the tangential component, and if we just concentrate, since only one component is y component magnetic field, that also I can solve using your wave equation, scalar wave equation, x dependencies and the propagation constant we can find out. So, whenever I solve using these components, I will be able to solve say so called beta Tm, and here I will be solving beta Te. If it is frequency same, we can write that beta C T equal to omega by C n effective m for T, and here this beta Tm will be equal to omega by C, same frequency, n effective m Tm. So, this m integer different and this m integer different. So, same waveguide it can support T polarization and Tm polarization also with a different mode index m. Okay. So, that is fine. Next, so I have defined NC cover refractive index, ND solid device layer refractive index, NS substrate refractive index, that is fine. But so far if I want to change omega, I want to operate which omega frequency we should use. Of course, we are interested around omega corresponding to omega if it is defined by 2 pi c by lambda, lambda equal to 1550 nanometer is preferred, that is the third generation communication window, that is fine, we can use this thing, but we have to see that any frequency if we want to vary, if I want to find out the relationship beta equal to say omega by c n effective, if I want to find out at different frequency what is the value of beta omega, it may not be just proportional, effective index can be also function of omega. So, I need to know at least that operating window, whatever material system we are using, that must be transparent, that frequency should see, electromagnetic wave should see it is a dielectric material medium. That means, it can be characterized only with the effective index, no sigma value, no conductivity will be there, no losses will be there, no band transitions will be there, photon absorption will be there, that type of things should be considered whenever you are considering frequency of the electromagnetic wave. So, in this system silicon on insulator SOI substrate, you have actually light will be confined in the device layer here, light will be confined, but you know the evanescent tail will be in the oxide and evanescent tail also will be in the cladding, top cladding, that can be oxide here, silicon nitride etc. will be there. So, we need to operate a frequency range which is actually transparent to top cladding, transparent to bottom cladding, transparent to core device layer. Core device layer is silicon in this case, in this example. So, crystalline silicon, if you see in this picture I have taken from some website, it is authentic one. So, if you see that the transmission of a crystalline silicon, it starts from about 1.1 around 1.1 micrometer. This is actually microns, wavelength in micrometer. So, 1.1 micrometer. Below that wavelength is lower and photon energy for that corresponding photon energy h cut omega, that is very high, and that actually absorb, electromagnetic will get absorbed and electron hole pair will be generated. Electron from the valence band, it will acquire energy from the photon, incoming photons associated with the electromagnetic wave for that frequency, and it will be released to conduction band. So, almost everything will be absorbed. Any intensity if you just fall in, I think most of the time depending on the thickness everything will be absorbed. That is why any wavelength lower than this, that means very high frequency operations. So, you will see that will not be transmitted, that is not transparent, that is opaque. So, it is not transparent. So, you cannot consider as a dielectric medium for that frequencies. But 1.1 micron to almost 9 micron, 10 micron region, 9 micron wavelength region. So, this is the broad band transmission. So, starting from 1 micron to almost a 9 micron, 10 micron wavelength, silicon is transparent. Okay. So, this is a good part. So, that means the core layer, as far as transparency is concerned, the electromagnetic wave has a broad transmission spectrum. So, you can use anywhere from 1 micron to 1.1 micron to 10 micron. Within that, remember that we have the third generation communication window as well as second generation communication window 1310 also it is falling within that. So, they are transparent. Okay. But if you just think of oxide is a different silicon dioxide, crystalline silicon dioxide. If you see, transparency actually starts from 0.2 micron. So, 0.2 micron about 200 nanometer wavelength, and it can transmit only up to 4 micron, around 4 micron here. Transparency is almost 100%. Here little bit there because there will be some reflection etc. will be there. That is why it is 60%, less than 60% showing, because Fresnel reflection will be there from the interface that has not been extracted. And glass, normally silicon dioxide, their refractive index is lower. So, Fresnel reflection will be much lower, that is why it is almost 100% it will be transmitting, and you will see transmission like this up to 4 micron. So, that means if I use a wavelength lambda which is beyond 4 micron, that may be transparent in the silicon, but that will be absorbed in the oxide. So, I can use up to 4 micron, which is actually from lambda 1 to 4 micron, I can say that. So, lambda can be less than 4 and greater than 1.1 micron. So, within that range it is transparent in both in the box region as well as in the core region. So, that is what it is very important whenever you are using silicon on insulator, what is the wavelength range of operation or frequency range of operation you should know. We know that this NC, ND, NS, whatever the refractive index, that refractive index whether it is a wavelength dependent or not or frequency dependent or not, we need to know that. That means whether the material dispersion is present or not. If so, while designing your optical waveguide, even though it is 1D or 2D whatever, you need to know the in a bulk what is their refractive index. Whenever I am just sweeping my frequency, I am solving the effective indices. For that I need to know all the every frequency range what is the refractive index. So, if you see crystalline silicon, it is shown because from starting from 1.1 micron it is above, it is there, this is the wavelength micrometer, up to 9 micrometer it is shown. So, refractive index, this is the refractive index, it is dropping starting from about 3.48 around 1.1, this is about 1.5. So, it is shown about 1.3 or 1.5 or something like that, and it is going like that. So, initially at shorter wavelength you see refractive index is somewhat it is falling means it is 3.48, 3.43. And then in longer wavelength it is almost stagnated or closing towards 3.45 or something like that. This is the refractive index is happening. So, if we operate at 1550 nanometer, it is about 3.4778, we have mentioned earlier 3.4778 at 1550 nanometer. 1550 nanometer. Below that it is a band gap absorption is there. So, they could measure, they could calculate from here up to here, and it is showing. A longer wavelength it is flat, but initially if you just change wavelength or frequency if you are changing, so you see some kind of material dispersion is there, frequency dependent refractive index. Dispersion means if any material, when a material is called dispersive, that means it is wavelength dependent refractive index is there, that means wavelength dependent phase velocity is there in a homogeneous medium. So, you see type of dispersion is there, material dispersion is there. But if you just consider, if you are concentrating only maybe 1500 nanometer to 1600 nanometer, very small range, 0.1 micrometer range. In this scale, within that 0.1 micrometer refractive index change is not that much big, okay, for silicon. Similarly, for silicon dioxide, if you see, it started from 200 nanometer up to 2.2 micrometer, it is shown in this graph. This wavelength it is shown. So, if you see initially up to visible region 800 nanometer, 1000 nanometer it is dropping, and beyond that it is dropping means it is dropping from 1.53 to 1.45 or so, and then after that it is almost nearly constant around our operating wavelength region. It is actually 1.465 something like that. This is the thing we are considering here, 1.45 or something like that refractive index. But here if you see, if I just consider 1400 to 1600 nanometer, refractive index is not changing much. So, I can consider it is non-dispersive around this operating wavelength range. So, whenever you are designing your waveguide, modes, everything, if there is a material dispersion is there or not, that has to be counted in your calculations. That much I just wanted to mention here. Okay. So, this is a material dispersion, and we have seen that how the material dispersion can be ignored or can be considered seriously, that I have seen, which operating or wavelength region of operation you are considering, that has to be kept in mind. But apart from that, what about waveguide dispersion? That is the major thing, the discussion point today. That means omega versus beta. That means this beta must be a function of omega, but whether that is a linear like this beta equal to omega by c n effective. If this n effective is not a frequency dependent, then it is a constant, then I would get beta versus omega is a straight line. But if n effective is frequency dependent, right, that means for a given mode this n effective or beta, they will become non-linear, and we have to take care about that if that is non-linear. If it is linear, that means normally we know that the group velocity and phase velocity will be identical. We will discuss that in course of time. In this case, we have to find out if waveguide dispersion other than this material dispersion, suppose I am considering that this Ns and Nd and Nc, so called refractive indices for the device layer, bottom oxide, top cladding, they are fixed, for example. They are not changing much as a function of frequency, that is fine. Does it mean the guided modes, that means n effective is also frequency independent or not? So, that is most important thing. Okay, that is what we want to see today. Okay, we take same reference again, that the silicon on insulator slab waveguide. So, cover refractive index Nc, Nd, Ns. We can always consider they are fixed. The material dispersion it is shown, but for our calculation we can consider that within the small window the material dispersion can be ignored, but actual calculation you should not ignore. I just take the reference of this one around 1550 nanometer. Okay. Now, I just put down the expression, typical expression for beta equal to omega by c n effective, and we know that this n effective must be greater than Ns and less than Nd. Nd is the highest refractive index, and any guided mode will see something effective index in between Ns and Nd. Anything beyond Nd never possible. So, if core refractive index is Nd, so any guided mode cannot have effective index more than that. It should be maximum can be equal or close to equal, it cannot be equal, it is near to the Nd, and but it should be obviously greater than Ns. That is what we have proved earlier also from the critical angle and Snell's reflection law in the interface. We have discussed many times that thing. So, this much you should be keeping in mind. Okay. So, what is next, and also TE-TM polarization, what are the components and how x direction confinement, y direction the y component, x direction for electric field also for T polarization, and its magnetic field for TM polarization we have considered. Now, we just go back again that the solutions, differential equation for T polarization we have to consider scalar wave equation this one, and for TM polarization we have this one. That is what we have already discussed. I just repeat it here, and kappa C, kappa D, kappa S we have introduced here starting from the vector wave equations, right, and effective index is the solution we just consider. Okay. Fine. Now, solutions, same thing I am just repeating here whatever we discussed in the previous lectures, that electric field Ui component for the TE polarization in the cover region, exponential decaying, and core region it is a sinusoidal, cosinusoidal, exponentially decaying. For magnetic field Y component also we have shown like this. Next thing, and we know that how to calculate also the other components for the T polarization, X component that is related to Ui component here, and Az component also related to Ui. So, once we know the Ui function of x, then we can find Az component as a function of x, and Hx component also function of x I can find. Similar situations also this thing I just write down the expression for understanding purpose. Here also you see you can find x component and z component, but whenever you are finding the z component you should keep in mind that additional thing is there. So, Ni means CDS. If you are using Ez component in the box layer, substrate layer, NS silicon dioxide layer, then this Ni should be considered actually NS value you have to consider here. And if it is in the core, that means Nd, refractive index will be Nd, and whatever value it is coming Hy, and you have to just scale it with the Nd square, that directly comes from your Maxwell's equations, nothing in our hand. So, that thing also consider here, it is Nc. So, we know how they are related. So, ultimately after solving one of the component, that is the dominant component Hy component Tm polarization, Ey component in the Te polarization, and then all other components we can find, and only thing is that N effective also we have solved their so called eigen equation we have used, and we have solved. That is again I just write down here eigenmode solutions. For Te polarization this is the expression, and for Tm polarization again if I just consider the boundary continuous here, boundary continuous here using these equations, then same way like Te polarization, if I solve for Tm polarization I will get little bit different equation, because here we are considering magnetic field. But that step I am not discussing here, you can take as a home assignment. Directly equation I have written, eigenmode solution for Tm polarization would be looking like that. It is almost same, but along with that Kc by Kd you see Nd by Nd square by Nc square comes here, Nd square by Ns square comes here, kappa S kappa D. So, that is the only difference of the eigenmode solutions. You remember that using this thing actually we could solve, because kappa C, kappa D all are actually N effective. So, they are basically transcendental equation, left hand side and right hand side both are N effective will be there. Here N effective will be there. If I solve this one, I will be solving N effective for T polarizations, and if I solve this one, I will be getting N effective for Tm polarization. That is it. So, both the polarizations they can have different, they satisfy different solutions. Their solutions are, equations are slightly different because their boundary conditions are different. In this case, Tm polarization you are considering tangential component of the magnetic field is continuous, and for T polarization tangential component of the electric field is continuous. That is why they are difference. These equations are coming from curl H equal to del D del T, all other components you will be getting, and here curl E equal to minus del B del T. So, from that we are getting all these components just discussed earlier. You just follow that. Now, how to solve N effective for frequency dependent N effective for mth mode. Okay. So, you have to use this transcendental equation for a given frequency. Here frequency is given, one frequency is given. So, you give a frequency value, this is the expression, right, beta equal to omega by c N effective, and if I give a particular frequency, I will be getting for that frequency what is the effective index for the fundamental mode. I can get that frequency what is the effective index of the first order mode. I can find what is the effective index of the this one. I can find out effective index of the. So, all of them for a certain frequency I calculate. If I change the frequency, obviously N effective, because everywhere omega is involved. So, I will get different effective index. Okay. So, changing frequency means for a fundamental mode itself. So, one particular frequency can actually excite different modes, but different modes, that is a certain frequency will be different, effective index will be different. But if you are restricting yourself only one mode and you are changing frequency also, you are changing the frequency, okay, you will get a different solution for N effective even for the fundamental mode. Even for m equal to 0, you will get different solutions. So, you can get solution by changing omega as well. Okay. So, once you know this, that effective index is relationship is this one, propagation constant relationship, you know that since your phase factor is this one, phase velocity will be Vp for mth mode, mth effective index will be there, beta value once you get calculated beta value, then you can get omega by beta m, and mth mode I can find what is the phase velocity. So, if different mode, if I am getting different propagation constant, they will be traveling with a different phase velocity. And if I am considering frequency is different, this beta m calculation also will be different. In that case, phase velocity will be different. Okay, fine. Next thing is that another important thing is the group velocity. So, group velocity is d omega by d beta m. So, group velocity meaning, suppose you know any particular frequency you are using, wavelength you are using, monochromatic things, that is a travelling wave it is going. But for our application purpose, particularly for communication, you have to encode the data. Time dependent some signal you will be modulating, and that is how you can use as a optical interconnect, right. So, in that case, when you start modulating time dependent variation, you are trying to on off something like that, that means you are, if you in Fourier domain you can see that it is a different frequency will be coming. So, in that case you need to see what is the how the group of frequency travelling. So, that group of frequency, that envelope, that information how it travels, that is decided by the group velocity d omega by d beta m. Okay. If this curve is not a straight line, beta versus n effective curve as a function, beta versus omega curve, omega beta curve, omega versus beta curve. If it is not a straight line, that means then phase velocity and group velocity will be different. If it is straight line, this omega by beta will be equal to d omega by d beta, right. Phase velocity, group velocity will be similar, but if they are not straight line, linear, then your phase velocity and group velocity will be different. So, group velocity, it is very important, because you need to know how fast your data will be transmitting. That actually gives you what is the flight time of the information, though it is very high, the close to because it is you are dealing with the light, it is the highest speed. So, but still you can say that how slow it is your information is moving, data is moving. So, group velocity is important. That is why it is important to know this dispersion curve, beta versus omega curve. Okay. Once you know beta versus omega, then I can suppose this is your omega and this is your beta, right. Then you get something, some solution like this at a particular frequency. You are getting, suppose this frequency you are getting here and this is here, you are operating in this frequency. In this particular frequency you have to find what is the slope d omega by d beta. So, that actually gives you, if this omega is your carrier, I can say that if that carrier is modulated with information, how fast that will be moving, that is actually group velocity. So, that is why omega beta curve in an optical waveguide is very important. What is the group velocity? Okay, dispersion. Good. So, next, what is that? You just try to find out what is the group velocity. From there, little bit you modify. I know this one. Suppose I know omega dependent n effective, omega dependent beta. Then, if I try to find out d beta by d omega from there, d beta by d omega, that means omega is there, this one. So, I can write this expression. So, if you see beta equal to omega by c n, right. So, now d beta by d omega, this is also omega dependent, that is why you have a two variable. So, I can write 1 by c, I can keep n first, and omega, if I just make a derivative with respect to omega, that means it will be 1, and then plus I can write omega and dn by d omega, right. So, this is the expression I will be getting, that is what I have written, okay, d beta by d omega. And d beta by d omega, if you see here, that is d omega by d beta is a group velocity. So, d beta by d omega will be inverse of the group velocity. Here we see 1 by c, and this one we represent as ngm. What is that? And ngm by c, c is the velocity of light. So, that velocity of light in the denominator, and this one some parameter which is actually defined by this expression, that is in the numerator. So, normally we can call this as a group index of the mth mode, because we know that Vg group velocity equal to c by ng, group index, right. So, this can be written d beta by d omega is called as a group velocity 1 by Vg, right. That means 1 by Vg equal to ng by c, that means Vg will be c by ngm. So, if you know light velocity of light, and if you can derive this expression, if you know the value of this one at a certain frequency, then I know what is the group index. That means, I need to know effective index at a particular frequency, and then I need to know that frequency, and I need to know what is the slope at that particular effective index slope at that particular frequency. Okay. If this slope is positive, then I can find this Ng is greater than N effective, if slope is positive. If it is negative, Ng can be less than N effective. So, typically most of the time Ng is greater than N effective, group index is higher than N effective. That means we know that when it is modulated, it will be actually moving slower relatively, phase velocity will be higher typically. Okay. So, now this is what we have written NGM. This NGM we are writing like this for the mth mode. If you solve mth mode effective index and mth mode this one, then it will be like that. But sometimes you know omega equal, you can write omega equal to 2 pi c by lambda, right, 2 pi c by lambda. So, d omega also you can just write, if omega equal to this one, d omega will be equal to 2 pi by c lambda square minus d lambda, delta lambda. So, if you just convert omega into lambda, then n effective minus lambda d n effective by d lambda. So, if you whether you can get effective index in terms of frequency or in terms of lambda, that does not matter, the group index you can calculate easily. So, once you know group index, you know the group velocity and you know the how your information travelling how fast. So, in this example, we have just tried to plot the omega beta curve, considering okay, this is lambda equal to 1550 nanometer, we consider this is the refractive index, and we consider this refractive index is constant for entire frequency span. That means, I have assumed that no material dispersion is there, and I have considered the device layer thickness is 1 micrometer stretched along x direction, and I am considering only T mode. T mode means I have only Ey component and Hx component, Hz component. For a mode, if a mode electromagnetic wave propagating as a mode in the waveguide, you have these 3 components, T polarization just consider. You can consider for TM polarization what is happening also, and you have this expression earlier whatever discussed, that expression repeated here, phase velocity I have written here, group velocity written here. So, I would like to know, I want to plot omega beta, beta is the propagation constant of a guided mode, okay, omega beta m for example I want to know. My expression is this one, I know how to calculate N effective, okay. So, I should be able to plot that one then. Okay. So, here this x axis is considered as a beta, y axis is omega, and in this picture if you see, I think so many things are there, step by step we will try to understand. So, this curve straight line is corresponding to omega equal to c by nc beta. Beta is the propagation constant, you know, if it is a homogeneous medium with a cladding refractive index NC, then any homogeneous medium you know, and there is no material dispersion. So, in that case omega beta relationship is straight line, slope will be c by nc. C by nc is the, c is the velocity of light, by nc that is the phase velocity of that particular medium. So, if it is a cladding material only, air, nc equal to 1. So, that means omega equal to c beta, that means omega by c beta, equal to beta, that means normally it is a k wave vector, it is a propagating like a speed of light, okay, omega by k equal to c. So, that is the thing. So, if we plot that homogeneous medium, in a homogeneous medium omega versus beta curve, that would be a straight line. Assume that as a function of frequency the material dispersion is not there. So, this is the straight line corresponding to this one. Similarly, if you plot omega versus beta in the substrate, you have this medium, right, you have a device layer Nd, and this is your Ns, this is your Nc, and I know that Nd greater than Ns greater than Nc. So, this is the case. So, if you consider instead of cover homogeneous medium, silicon dioxide box layer, that is continuous, then you get another straight line. If it is homogeneous medium I am considering, so you will be getting this thing. And same thing if you are considering for a core, if it is a silicon medium. So, this is your beta, this is your omega, that will be again straight line. So, such a plot in a homogeneous medium, that is a straight line, they are normally called as a light line. light line. So, this is the light line, this straight line is the light line for silicon as a homogeneous medium. If you are allowing electromagnetic wave propagation in a homogeneous silicon medium, then this is the light line. Any frequency consider for that light line, this is the frequency, and if you take this one is the beta. So, omega, whatever the omega value, this is omega value and this is the beta value. If you take omega by beta, that will be c by nd. So, that is the phase velocity of that medium, particular medium. So, similarly, this light line you consider for the box layer. So, you can consider your velocity is the omega by beta equal to c by ns. So, this is again like this for the cover medium, fine. Now, you know that your N effective is going to be less than or equal to Nd, greater than equal to Ns. So, any solutions you get for any frequency range, that will be something like beta. If you just write beta equal to omega by c N effective and omega equal to c by N effective beta. So, since this N effective is less than Nd and greater than Ns, so N effective solutions will be coming in between these two light lines, light lines for Nd, light lines for Ns. In between your N effective will be there. So, any solutions for N effective, that will be in this region. Between these light lines you can have a N effective solutions. And we have seen that if you are considering m equal to 0, then you plot that earlier equations, whatever the equation you have considered, this kappa d h equal to m pi tan inverse plus tan inverse, that equation we have explained earlier, that is the eigen equation for solving effective indices. So, m equal to 0 if you put, you get this m equal to 0, this curve you are getting. This is almost starting little bit higher, and then as you increase the beta value or omega value, it is merging towards Nd, because effective index slowly it will be merging towards, as frequency increases this way, then it will be going like that. Similarly, for m equal to 1, you get another relations, omega beta relations. Omega beta, these are the curves for this one, for different mode. M equal to 1, you are getting this curve, m equal to 2, you are getting this curve, m1, m2, m3, m4, 4 curves you are getting. So, you are getting 1, 2, 3, 4, 5 different curves it is plotted here. Okay. Now, 5 different curves, you can get a solutions from that, and you consider h equal to 1 micrometer, 5 different things, but ultimately we know that for h equal to 1 micrometer there will be 4 modes. We will try to explain where is the 4 modes coming. You know, this value, this frequency is corresponding to 1550 nanometer. Okay. This is the frequency, and if you go in this direction, then you see it is actually cutting m equal to 3, m equal to 2, m equal to 1, m equal to 0. That means, I have one beta solution, another beta solution for that frequency, another beta solution here, another beta solutions here. So, these are the 4 different beta solutions I will be getting for this frequency. Silicon on insulator slab waveguide, again example we are talking. We want to know a mode. Suppose a waveguide having h equal to 1 micron or so, or 2 micron, or maybe even less to 50 micron to actually 1 micron, that is not standard. I just considered here for this calculations or understanding purpose, that okay, this is something can be 1 micrometer. It can be less than that, as I mentioned earlier. H can be as low as some 100 nanometer also. We will see that later. So, I would like to know, suppose there are several modes, they can different mode will travel with a different phase velocity, that is one thing, but their group velocity also can be different because of the dispersion omega beta relationship. But a mode, I would like to know how much energy it is carrying by a mode. I would like to know, for example, how to calculate that. You know that Poynting vector, this is Poynting vector means, that means Poynting vector is defined by power flow per unit area per unit time along the propagation direction. Energy flow, this is a power, not energy flow, I would write energy flow. Energy flow per unit area per unit time along the propagation direction. That is actually Poynting vector. Okay. And normally along the propagation direction, if it is a transverse mode, that is why it is E cross H. And we know that we have discussed earlier that if you are using E and H complex, then to take average, time average, you have to take E cross H star, and then real part you have to consider, and you have to multiply by half. Then only that is actually actual real value power flow per unit area per unit time, energy flow I would say. And so, energy flow per unit area is a power basically. Okay. So, if I just expand this cross one, E cross, this is a vector A, this is a vector B, and their cross product we can just express in this form, right. A x, that means unit vector along x direction, unit vector along y direction, unit vector along z direction, and the first vector E x, U y, E z, and H x star, H y star, H z star. Okay. Now, since our waveguide is aligned along the z axis, that means mode is propagating along z axis. So, that mode will carry energy or power along the z axis. So, that means I only need to concentrate what is the power flow along z direction, z component, this is a vector basically. I need to know this power along z direction. Obviously, if you just calculate say this is actually P z, if you calculate P x also, average x, you will be getting also some value P x, but P x this direction whatever power goes and back reflect back, that actually creates the mode. So, that will not carry energy along the x direction, you know along x direction evanescently decaying field. So, that direction no energy is being flowing. So, only energy flow that is happening along z direction, right. So, in that case z direction, what is the Poynting vector, I could express like this. So, this is z direction means this one goes, that means E x times H y star minus E y times H x star, and real half is there. So, we have written accordingly. So, this is the, if we know the components for a given mode, then I know how much power flow or energy flow per unit area per unit time along the propagation direction we will be able to know. So, let us concentrate for T polarization again. T polarization, these are the components. This is the components. I just consider U y. U y can be expressed like that. X direction, some field distribution will be there. That for T polarization, we have the field directions, field components, and then y component we express as a function of x, and then propagation direction beta is there. Beta can be expressed by this, and the field distribution in the upper cladding and in the core region, bottom cladding it is there, and we know that for this purpose I need to have some energy flow in the z direction. We need to find out what is the other components, magnetic field H x, H z. I know that from the Maxwell's equation H x and H z component, they can be expressed, they can be derived once we know the y component of the electric field, that is what is written here. So, now for the magnetic field also likewise, I can define y component of the magnetic field in the cover region, core region, and cladding region, lower cladding box region, and other components like E x and E z, again we can derive from the Curl equation, Maxwell's Curl equation. That expression I have shown earlier also. This is the straightforward just from the Curl equation, and we know that this kappa c, kappa d, kappa s, they are defined like this, that I repeated here. Okay. Now, what I will do, I know that z component, z direction, this is the power flow, energy flow per unit area, right. So, now what I will do, let us concentrate only a T mode, T polarization, where I have this component and H x, H z, right. So, if I try for T polarization, you do not have H y component, H y component is not there, or E x component is not there also. E x component is not there, H y component is also not there. So, this part will not be there for T polarization. So, for T polarization I can write this one, this is the expression, half real part minus sign u y h x. H x can be expressed in this form. So, if I just, because I solved E y everywhere, now H x can be solved from the E y, just you have to multiply minus beta by omega 0. So, if I just replace H x here, this H x I can just put here, this one here. Then if you just multiply here, then you get x dependent energy flow per unit time per unit area I can write. If I want to find out what is the energy flow in the z direction here in the top cladding, whatever the field E y x is here, I have to use this one here, coordinate system accordingly. Core region E y x is differently defined. So, that means E y is different region is different. So, I can find out what is the intensity or energy flow per unit area per unit time here, what is the energy flow per unit area per unit time here, you have to use this equation here. And if we want to say whatever energy flow in this direction happening, because you have evanescent tail, it will not carry in x direction, but this evanescent field can carry energy in the z direction. So, whatever the field strength is there, you just multiply, square it and scale it, then you can find whatever energy flow in this direction. That is why your mode, your energy can flow not only within the core, it also can carry energy in the cladding region only along z direction, but not in the x direction. That is why it is evanescent tail. Now, similar thing for TM polarization. For TM polarization, I have, this is the actual energy flow coming from Poynting vector, where for TM polarization we have E x, E z, and you know what is the value of H y, that is the expression you have solved, H x, H y x in the top cladding, H y x in the core region, H y x in the bottom cladding region. I know these are the expression we have solved, and from the Maxwell's curl equation we can express E x and E z component for the TM polarization. So, for TM polarization what is missing? We do not have E y component, that is 0, and we do not have H x component, that is 0. For TM polarization I will have the energy flow per unit area per unit time is E x H y star. So, H y star, I know H y expression everywhere, I know H y, and E x expression I can derive here, using that E x I put here, I can express the energy flow per unit area per unit time in terms of magnetic field component, tangential component, because that is the solutions I have. All the position I know what is the energy flow, intensity, everywhere intensity flow in this direction, z direction I can just find out, okay, but in terms of H y. But remember that when I am just calculating for T polarization, beta by omega mu 0 here is there, but in case of TM polarization this n I square, because you have to consider this refractive index whether it is in the core region or top cladding or bottom cladding. Accordingly, it will be placed n I, it will be considered n c square, n d square in the core region, n s square in the substrate region. So, this region, all this thing, 3 different region energy flow, that also depends on what is the dielectric constant there, not only field distribution, magnetic field distribution. Here we are considering electric field distribution, only E y component, here magnetic field distribution we are considering. That is the reason we need to consider what is the dielectric constant here, that directly comes from your Maxwell's equations, you do not have any other reasons for that. So, all this expression involved in that. So, once we know that energy flow per unit area per unit time, okay, I want to know, because your field is distributed throughout evanescent tail to core region everything. So, total power how to calculate? What we have to do? We have to integrate. So, that is the reason whenever I am just written down this expression energy flow 3 direction. So, integration. So, this integration I have just considered also along y direction, because waveguide you cannot have just one dimension, just x direction confinement, but y direction I have just so far considered is infinitely extended. So, but actual calculation how much power will flow, so you have to consider, okay, up to what some extent, though this is basically everything ideal along y direction. So, we can consider dy as 1 micrometer, 1 meter for example, or 1 nanometer, 1 unit. So, in that case I can say that per unit length, because I assume that along y direction this component is not varying, that is our assumption, H y component is not varying along y direction. along y direction in also not varying, only x direction it is varying. So, n square x I have written here. So, if I integrate, suppose this integration will have 3 different functions, this function will be different. So, I can just decompose into 3 parts. In the top cladding I have to use this expression and I have to integrate. So, I can just integrate this one and this one. So, first part is this is minus infinity to 0, x equal to minus infinity to 0, and then second part that will be 0 to h. I will be using this expression ui here, and I will be using third part, that means h to plus infinity, that expression I will be using, and everywhere I should use. Then only I can find out, because evanescent tail, if it is some penetration depth is there, but it will be extended theoretically exponential term, it is extended up to infinity. That is why for integration purpose I can use this limit. Then I can find what is the total power that is flowing for a certain mode. If I just consider a solution for a certain mode, I will be writing that particular mode, that beta value for T polarization. If it is Tm polarization, you solve beta m, then you can calculate what is the value for the power. Okay. And little bit of modifications. So, this expression, if you just do this thing beta equal to, you write omega by c n effective m for T polarization. If you just replace that one, omega mu 0 and mu 0 epsilon 0, you know that mu 0 epsilon 0 equal to 1 by c square. So, all these things if you do, then you can little bit modify this expression like this in terms of n effective and eta naught. Eta naught, you know that that is a intrinsic impedance for mu naught by epsilon naught, this one. So, we know that power carried by a mode. To estimate that, you need to know field distribution throughout cladding region and core region, and you need to know the effective index of the guided mode. If you know that, then you can find out obviously how much power is flowing. Of course, in this E y mx, you know Ed is there. Ed is the constant where we consider most of the time 1, while plotting the electric field distribution we consider 1, that is normalized to 1 volt per meter, for example. It can be 5 volt per meter, depending on that it will scale up. And once you know normalize Ed1 with respect to Ed, you know what is the relationship with the EC, you know what is the relationship with the ES from the boundary condition. So, you will be able to know. Only thing is that you need to know what is the value of Ed. So, if it is just you are considering normalized one, you can consider 1 volt per meter. Okay. And dy, if you are considering watt, that means we can say 1 meter, then we can say that power flow in by the guided mode, it will be watt per meter. Watt per meter means 1 meter we are considering along the y direction, and x direction I am integrating everything. So, I can calculate what is the power flowing, power carried by the mode. So, this is very important. I will be discussing for the 2D, when we will be discussing for the 2D waveguide, that y direction also some distribution will be there, that time y limit also has to be considered. This 1D waveguide is very much ideal case. So, ideal case, though it is ideal, but we are getting entire clear picture how the mode will be there, how that will be propagated, and what would be their relationship, what is the dispersion relationship, what would be the group velocity, everything we are getting. But obviously, this is a ideal situation where y direction we have considered infinitely extended, which is not practical though. Okay. So, this is the relationship we are just writing finally. Okay. This is the final expression. So, this part, all this orange color part is the corresponding to TM mode, and all the green color part expression together, it is summarized here, all the electric field distributions and other components, magnetic field, corresponding magnetic field, and here for TM polarization you have the solutions and corresponding electric fields, and power, how much you can calculate, how much power it will be carried, that can be calculated, and for T polarization also how much it will be carried, we are also able to express. So, this is where this is how we want to close the discussion on 1D optical waveguide, and we have taken only for silicon on insulator platform that is basically as you buy, that is commercially available optical grade, as you buy they are giving you just 1D waveguide already. But this 1D waveguide is not so practical for integrated photonics purpose, because you need 2D confinement, photonic wire you need for optical interconnect. So, we need to now discuss this 2D waveguide, how 2D waveguide can be designed, what is the theory involved on that, and what are the other additional things you need to consider, that I will be just discussing in the next lecture. Thank you very much.